Good evening. Okay, good evening, everyone. We'll wait for some time and let the other join, then we can start the session. Some 4 or 5 minutes. Yes, good evening. Uh, like, shall we start or will we wait for some more time to let other join? Okay. Good evening, everyone. My name is MD Sidraza, and I'm PMRF scholar at Trichapalli. And today we'll be going to take a session for machine learning for engineering and science application. And today is the last session. Like we were doing from the last 12 week. Every week we were having the interaction session and the problem solving session. And today I'll be giving some brief how it started, and will give the quick revision also, and we'll solve we'll going to revise again same problem like what we have done in the that last 12 week. It will be just a quick revision only. So I think just any doubt before going into the session and all, any doubt is there that you want me to clarify? And hopefully that all the assignment that you have submitted on the portal, and feedback form is also there available on the portal itself. So hopefully you just fill it out for the every week, like how the session went, and where that team member can improve for the NPTR interactions and all, and how we can make impact better. Okay, so Actually, this course is actually that is the like machine learning for engineering and science application, and this is the fundamental course. Actually, I can say like basic course. Like it's going to cover the broad topic. Like it's deep learning, also supervised machine learning, that the neural network, or some advanced topic also like generative AI or auto encoders and all. And we have seen some example in the that was the yesterday class only. We have seen some example in the engineering also, example like fin, that is heat transfer, how it will happen with the time. So that we have checked with the neural that network also we have checked. Second example we have seen with the fluid flow, or maybe the heat transfer in the computational fluid dynamics also we have seen. And for that also we have run the model that is called neural that network. And even we have given the contour of the flow velocity as an image, and we have trained the CNN model also, and we explained the CNN architecture also. Then third problem was the optimization problem. Like it's a topology optimization, like how like material distribution can be there. It should be like sturdy enough or strong enough, and then it can stand with, and then it we can optimize, we can save the materials also. Saving the materials itself, it will be optimization also. And last problem was that based upon the ODE and PD, like ordinary differential equation and partial differential equation, that we have solved around. So before that, before like in the last week, it was the cardiac that MRI image and all, that was especially like exclusively for the scene examples and all, like MRI for the cardiac applications and all, that we have seen around. So now like today, I'll just give the starting from the brief, and will where and how it will go, and then we'll see what are the problem can become like for your final exams and all, exact pattern and all, whatever that we are getting in the assignment, the same way it will come also. And it will be not doing the code basis. It will be mostly that theoretical basis will be the question will be there. Like let's say that how the trade and trade between that bias and variances that's happening, or maybe in the physics that inform that neural network, how that other parameter will get affected, and all that all will be most of the subjective question will be there, because it's a computer based examination and all. And subjective might be not there, like mostly it will be not there and all. So okay, we'll go ahead with the our starting, we'll introduce the session and all, and then how it will go. So as we know that if we go with the traditional machine learning application, I'll just open the camera here. Hopefully there will be no any doubt, or you don't have it. If you have some doubts, you can just text here, or either that you can ask directly. We'll solve it, or we'll clear it. Okay, so if I'll go with the typical that definitions of that machine learning, it's that machine learning aims to that replicate the activity that required the human that recognition. It's a human brain. So they will try to replicate the human that's the human activities and all. Let's say that the machine itself, machine doesn't they're not going to so they can't take the decision by their own, like just as a human being we can take the decision by our own, but machine can't take the decision. So what they will do, we have to train it. We have to train the machine, or we have to give the some information to take the decision. It's not like they're going to take the decision by their own. So that machine they're going to learn, or they're going to, either we have to train it. So if you see that where it going to take some examples and all, if I'll see around. So we'll go with the real-time applications also, like traffic predictions and all search engine results. Also, like it's now in the Google Chrome and all, they're coming with the AI mode, or Gemini itself, like they have incorporated in the search engine itself directly. Even earlier that, but now also we are having the spam detection, that email that going, and like it's either spam or not spam. So it's neo-based classification also people are doing with the based upon that also. Even they're doing with the medical diagnosis also. I just took all the slides from the all last 12 week, and then I have summarized it here. I didn't add any single that new things here. We'll try to just quick warm up, I can say, or revision that will going to help for your final exams and all. So, and even that we can use for the text and speech recognition also, like translation also, we can see email is that is spam filtering also, we can have the example, and image recognition also, when we have the ad as in the car and all. So we just 1 minute. Yeah, how to solve the transport conversion problem that we can will explain to you like how we can solve it and all. Like it's a extension of the scene and all. Will explain to you. Okay, so we'll go slowly. So we start like just introduction only. When programming a computer was first conceived, we were people were wonder why that such machine might become intelligent and over a 100 year before it was built and all. So the today artificial it's going to filled with the many practical applications such as intelligent software to automate routine labors, understand the speech or image diagnosis and even in the support basic scientific research also. So that machine learning it's a field of study that give computer to learn without explicitly program. Like we don't have to give the programming and all. Instead of that, they are going to learn through the what we can say training or maybe the previous history. So if we go with the how it went that their history of that applications actually, if we talk about if you have seen like one movie that based upon the Alan Turing test was there. I forgot the name of the movie actually. Turing test was that was to decode the message from the Soviet Union. Like that one only like we have to decode the message that was used in the like after or maybe we can the Second World War also. And then that was the neural network in the that like 1975 and again in the ELIJA that developed by the MIT in the 60. Then we went ahead with the KNN in that 97 like 1970 and then back propagation takes shapes like it was the till here it was the forward propagation based upon the finite difference method finite difference methods only. Then it came to the back propagation that in that we are using the chain rule method like we are going to take chain rule of that multiplications and all. Just 1 minute. Yeah, please. You have raised the hand.
Sir, can you guide how to clear the exam or how to prepare for the next week exam?
Exam guiding, it will be like you have to clear with the basics actually. I can't tell like how to clear them, but I'll tell you so that the basic behind you have to go through the all the algorithm. Like in KNN, like what is that like algorithm that worked on the CN tree also, what is the node and all, and then CNN also what is the purpose of the striding or the pooling or that max pooling or maybe if you're going through the SVM, but it worked, but not worked, that type of serum. So if I'll just show the some assignment problem if you have solved the assignment problem, the similar way the question will come. It will be mostly based upon the subjective, based upon the theory itself or maybe the concept itself. Like it will not go, so they're not going to ask the coding or to get the accuracy and all. If I'll open the what I can say. Just 1 minute. Let's say I'll take one simple example like first week. First week, what we were having, we were going through that basic algebra, basic operation, and then even with the like algebra concepts and all. So their assignment was something like how this is that 1000 by 9 into like how we can get the like that matrices and all. So you can just check it out like 1,000. It's the input like it should be their input. Like they should have the inside size should be same like m by n into n by m. So that that outer will be like outer will be out and then inner like m by n into n by m. So that will be 9 by 3. So we can get here like 9 by 3 itself. So that's how the things will go. The second one, what we have, it's the solving the simple equations itself. So it's based upon the what we went to the lectures, what we explained the basic operation of that matrices and all. And if we go to the jumping into like let's say that the linear regression problems and all that we have seen in the fourth week, and their example, the cues, that assignment was something like this was there. So they will be asking like given of the n m data, suppose we have that like what will be for this particular, what will be the Jacobian and all. Again, it's based upon the transpose and all that we can see around. Even they are saying we might why might we resort to numerical methods such as finite difference or the automatic differentiation to calculate the gradient instead of analytical method. So why it required? Because we don't have the explicit expression and all. So it's based upon the theory itself. Okay. So this is the how the question will come. So you just go through or try to get basic clears for the exams and all. Hopefully that is clear.
Yes, sir, clear. First, we have to solve the all the assignment problem, but there may be large calculation in few problems.
Last calculation, like sometime you have to solve the like that the numerical also. So if mostly numericals will be if it is there, so they'll be given the scientific calculator that will be within the computer itself. Scientific calculator will be not allowed today, but it should be like a computer. But I don't think so. There will be a, like to solve the numericals. It will be based upon the like if you can do it by your own, that much that level will be there, not to very like calculative that theory will be like that the numerical will be there. Okay.
Okay, sir. Okay.
Okay, so we'll go. And one question regarding was there like how to solve with the transpose convolution. Like it's something like we have like very lesser input like that is a map feature, but we have to generate the feature map would be like much more higher than the input. So in that case, we have to use the transpose convolution and all. Like I'll tell you the like detail once we'll go with the CNN part and also. Assignment 6, question astronomical calculation, option C is correct. Okay. For this week only, like fourth week. This is the last year question, not like this year one. This is not for this year actually.
Sir, this is
Yeah.
in the current semester, current year.
No. This is last year actually.
I am asking for assignment 6, question number 10. This year only.
This year only. Okay, I'll just check it out. They might have all given the. Assignment 6 solution is also
Yes.
given for the
Yes.
this year.
Question number 10.
Yeah, yeah. It's a detailed solution is also given. I don't know how
Not
come.
given, sir. Just given the answer.
Yeah, here. What is the output of the transpose convolution on the I plus k with the stride 2 padding I? So we can see around here. The output size is like some 3 into 3 in 3 minus 1 into 2 and all. It's a 4x4 input. And in a transfer convolution with each input value is multiplied by the kernel and stamp into the output at the corresponding stride position. So with the stride 2, so we have to take the adjacent element with the two position 1 2 1 2. Let's say applying the kernel. Let's say I have 1 2 padding of 1 to 1 to 1 2 can go. So to each of the input element I accumulating the onto a zero parity output grid. So the final result will be like this. So analysis of the option B, C content correct option. Where it went wrong, can you just tell me?
Sir, when I solve that problem, I
Yeah.
get the answer option C.
Okay. 3 2 1 8 12, 14 12 8 9 17 18 14 8. Okay. 4 12 and all. But once you do the padding and then that the max pooling, that I think you will get the option A only. I'll just see. I'll just solve it out.
Not max pooling, but it is after padding each element of matrix I multiplied by with the kernel
Okay.
and place in this position, and outer rows and columns will be eliminated, and we will get the 4 is to 4 matrix.
Yeah, first of all, we'll get it.
Yes, sir.
Hmm.
One second, sir. If you permit, I can show the solution.
Okay, fine. Just show me. Otherwise, we can raise the issue to the like that you can into
I
the
have
forum.
raised this question, this problem in the forum also when this assignment 6 solution will be released.
Okay.
So at that time, I also raised that problem in the forum also. But
Okay.
nobody responding that how it is calculated.
Okay, fine. We'll just check it out. Like that you can present it and show it to me. I'll just stop it.
So I got my answer as 3218 14489. I didn't write the option actually.
Okay.
78418 and 242440.
Sorry, I didn't. That I didn't get it actually. Can you just tell me again?
My answer is 3218, this is the first one.
Okay.
14489, 78418, 242
Like option C.
Option C is the correct answer.
Okay. Okay. If it is there, then I'll from my side also I'll
I guess they have considered the. I'm not sure, but we got an email that marks to attendance system. So we checked, we evaluated.
okay.
I don't know about this question, but I also know that it is company.
Mhm. Okay, fine. I'll do one thing. I'll just raise the same there also. We'll try to figure it out. Okay. So we'll just go recap fast enough. Okay, so but the difference this time, like we have the better technology, huge computational power, and even with the big data. Earlier, what was the issue was the like we were that is going to lag in the our what you can say that computational power actually. But now we have the NVIDIA graphics and all, big data, and then democratization of the software or maybe the hardware is also better algorithm also. So we have the some two, three terms are there like artificial intelligence, machine learning, and deep learning and big data. So what is the difference? We'll see with the Venn diagram. So like what the people have the knowledge basis. So that will tell like it's a broad AI term. AI like it's a fully like we'll be having the like that example like that will have the knowledge basis of the machine learning, deep learning, or maybe that repetitive learning and all. And if we go a bit of a specific like logistic regression and all that will go around that like will that is machine learning is part of the AI actually. And the representation learning it's again the shadow encoder like will try to replicate and all. And then third one what we have is the deep learning like it's a sub part of that what we can say that the machine learning and all. So that is the AI. It's the broad, like in that can we have that expert that knowledge basis. That the machine learning it's a subsection or subset of the AI, and then followed by representation learning, and then deep learning and all. So now the things like how it went, like we what we have it's the real based system, then high design program, and then output will be the this is called like it's the classical systems and all. And then we will be having the classical machine learning problems will be like input is there and this style and then mapping from the feature. Like we'll be having some features will be given and then we have to get the output and all. Then third one is the representation learning. Like will be input features mapping and then output one it is separate. Then again sample feature additional layer or abstract like it will be coming together the deep learning and all. And then mapping the feature then output will be there. So what is the machine learning? Like it's something we have to classify or we have to get the pattern and something like if you go with the formally some example like a computer program is set to learn from the experience E with respect to some class of task T, performance measure P, and performance at task measure by like T as measured by P improve with the experience of E. Like what they try to say, a computer program they are going to learn from the experience E. They are going to with respect to the class task T, and then we have to measure the performance P. So if it is performance at the task T, like at same so for the same task measured by P improve with the experience like something like we have to get their accuracy or maybe their performance like improved with the help of the machine learning and all. That's how the things will go. So human can learn from the past experience by making like make a decision by their own, like we don't need to give some input or training and all. And what they will do, what is this object, like people can say that as a human being that we'll be able to say and all. And but this objects will be able to make the decision by our own. And so it is a car actually. Okay, it is a car actually. Just 1 minute. Okay, so it's a car we have make the decision by our own, and let us ask the same question to him. What is the object? So they will be like, but teach human beings so he can observe and learn. And the thing is that let us make him learn, show him, and then we'll be having the car, bike, and then bike. So the same question will ask, so they'll be able to say, oh, it's a car. But what about the machine? Machine follow the instructions, but they can't make this like a decision by their own. So what they will do, we have to give the to perform an arithmetic like we have to give some instruction like 2 plus 2 is equal to 4, or maybe two into 2 is equal to 4. What about a machine that they are going to make the comparison, print it or plotting a chart? So what they will do, like we want to machine act like a human. So to identify this object, so we have to predict the price in future, or maybe we have to we have to make sure like it's price of that in future is 2025, or maybe I made him yesterday, like it's something like we're just making sure like they're going to learn. So even they will be able to do like recognize the faces also. And then what do we do? Like just like what we human do. So we need to provide the experience to the machine. So how we'll do it? Like we have to give the input in the forms of the binary machines and all. So it will be based upon the data set. Like will be given the some data set like car, bike, and all. So what they will do, like it's a data set. We have to provide the data set on the on to the machine, and then divide the algorithm and execute the program on the data. So when then we will be asking to respect to the underline the task. Like we have to ask them to learn it. So then after what they will do, like they're going to this is the machine, that this is the data set, then algorithm, then they're going to identify which one is the, like they'll be going to extract some required pattern for the same. So then they're going to identify the like that the relation, they're going to make the decision. So this is the whole process of the machine learning and all. Like it's the machine they're going to learn. So in summary, what they'll do, we are going to give identify and create the appropriate data set, perform computation to the learn, required rules, pattern and relation, output to the decision, machine learning paradigm. Like we have the machine learning, like supervised machine learning, unsupervised machine learning, and then we have the reinforcement learning is there. So if we talk about like how it worked in the machine learning paradigm, like it's the rule. Classical programming, like what we have we know the rules, we know the data, we'll get the answers. But here we have the data, we have the answers, like we know the what is the input for the machine learning. We know the input and we know the output. Now we want to know what is the mapping. Okay. So when machine is not going to when is machine is going to like useful when we don't know the rule and when they clear. So when the experts are unable to expert their expertise, image recognition, stage speech recognition, driving a car, when humans that human expertise does not exist, like hazardous environment, navigation on the Mars or maybe the bad weather, our solution need to be adapted to the particular case like biometric or like a patient specific treatment and all that. In that case, we can use the machine learning and all. So if you go with the what are the types of the machine learning we are having, it's a that like that's a supervised machine learning, and then reinforcement and unsupervised machine learning. Okay, so it's again different types. Like we are having classical machine learning, supervised, unsupervised. In supervised, we have the regression classification. In the regression, we have the that the uh, l- linear regression, then the polynomial regression, and then ridge and lasso regression. Then classification, we have the KNN, naive Bayes, SVM, decision tree, and then Loessner regression. And in unsupervised, we can do with the clustering. Clustering also we have a k-means clustering and fuzzy xenon and agglomerative DBA scan and all. And then pattern search is there, like we are having the PP growth and all. And then we have that dimensionality reduction, like when we have that more number of dimensions that might be confusing for the to the machine. So we are using a like a TSNE, PCA, LSA, SBA, and then LDA like a dimensionality like reductions and all. Then we have the ensemble method, like it's the bagging, boosting, and then stacking is there. Then reinforcement learning is the genetic algorithm, and then Q learning and all are there. And then we are having the like that's the neural network. In that we are very powerful. It's the CNN. Then MLP is the multi-layer like a perceptron autoencoder, and then generative adversarial that like that the network is there. Then RNN is there, like when we have the time series data is there, is there. Okay, so this is the brief types of the machine learning. So what are the types, like what are the steps that we'll be having in the machine learning and all? Like first one is the to data collection. So once we have collected the data, we have to data preparation, like we have to clean or transform, like either we have to make the data labeling, we have to make it. Then we have to, according to the data or according to the whatever we need, like output and all, that we have to select the algorithm. Either it can be a classification, it can be a classification, or it can be of a regression problem. And that appropriate model will going to choose it out. Then we have to make the model training, like data set divide, like train and like train or test split. We have to make it out, and then validation also we have to make it out. Then we have to make the model evaluation using like a performance parameter. It's something we'll be having for the classification. We'll be having like accuracy. Accuracy will be there. Then we'll be having R1 is precision, recall, and then for regression we'll be having root mean square speed. No, root mean squared error, and then we'll be having the mean absolute error, then coefficient of determination, or then coefficient of coefficients and all will be there. R square and R value will be there. Then if it is not there, so we have to make the hyperparameter tuning also, model improvement, like by doing the fine tune optimization. Then we can do the deployment. This is the some basic steps in the machine learning what we have. So now we'll come to the mathematical idea that are going to be used in the machine learning, because machines they're not going to take the raw into the form. They need the, like in terms of the number that is done through the linear algebra, like by in the matrix form, like it's a binary and all. Then we have the probability, like it's to make the uncertainty or chances of the occurrence. And then optimization, like we have to do the which for which parameter the model is best. These are three steps that we have to make it out, like before jumping into the actual machine learning SO. So while that the linear algebra is going to useful, like we have to make machine learning algorithm that required input and output are going to represent in the vector form. So it's a simply collection of the number, like it can give either matrix or tensor if it is like that higher order form and all. So part of the problem is to convert seemingly qualitative input such as picture, sound, color, etc. into a numbers. So why it's going to use, like it's for a black and white image we can give the intensity, like let's how it's work it out, and we can keep on image intensity number. But for a color we have to give the RGB pattern and corresponding numbers. That's how we have to give it out and all that, like because simply giving this image it will not work it out, like the machines will not going to understand like how it's going to work out. Let's say this is a tube, that is the one LinkedIn post is there. This is the one X-ray or MRI image is there. So what we'll be giving this directly image, it's not going to work it out. We have to convert into the tensor, and then we have to train the model. We'll be giving the session like same in terms of the in the tensor itself. And then from that, we have to extract the features, then we have to get it out. So that linear algebra, like it's something like we're going to use for the either for the continuous rather than like discrete mathematics. Many computer scientists have like little like experience it. Like we have we can use in the science also, engineering also, and that we can use for the either both like continuous also maybe and then discrete also. So a good understanding of the linear algebra is going to helpful because we have to calculate like we have to convert the image or any input into the like that numbers, so that it's going to help with the machine learning, especially with the deep learning algorithm and all. So what about the probability? When because the thing is that when we take the data set and all, it's going to have the repeated that number of experiments will be there and all. So that need to be checked with that whether it's a deterministic or it's a probabilistic and all. We have to check it out. So if an experiment is repeated under essentially homogeneous and similar conditions, we generally come across the two situations. So the result or what you will known as the outcome is going to be unique or certain, and the results are not unique. So then maybe one of the several possible outcome will be there. So that can be check it out with the probability. So as we can see around here, like it will change with like a deterministic model is something which stipulate that condition under which the and experiment is performed, that outcome will be it's going to be stipulated, like it's going to be we will know that that will be the that will be the outcome will be there. But in the case of probability, it will be some sort of measure of uncertainty will be there. Let's say I'm going to flip the coin, either the head or either the tail. There is a certain there is a certainties are there. So there is certainties are there, but but the thing is that there is chances like uncertainty will be there. Like when we flip the coin, it's going to make the sum either head or tail. Means there is chances of the 50-50 percentage and all. And some rules of the probability, like we have the commutative law, associative law, distributive law, complementary law, and then difference law will be there. And we have the one problem, it's a Bayes theorem. Bayes theorem, if I'll see around, Bayes theorem is something like we'll be having the one event that already occurred. Now, like it's something like one event already occurred. What is the probability of the upcoming event when the one already occurred? So that's how the Bayes theorem is there. So let's say it's one event that already occurred. Then based upon that, we have to make the decision for the upcoming or the posterior probability and all. So what are the types of the variables will be there in the probability? One is the discrete discrete random variable. For that distributions will be having the PMF. It's called a probability mass function. And for the continuous variable, we'll be having the PDF like a probability like density functions and all. So what is that discrete like a random variable is something either 1 or 0. Maybe that PDF is something with the time it will be going to continuous way. So machines, how can we give it to the output that the machine will take only input as a either 0 or 1 itself. It will not take like other. Until unless we have to make the like a sophisticated machine type, like it's a 0, 1 or 2, it can go, but it's very difficult. But in the case of that our machine learning paradigm, we can give the multi class classification, but for a machine that's very rigid, like it's a 64-bit also or 32-bit also, we'll be having only two, either 0 or 1. It's a binary form. In that only overflow, underflow can happen. That we have to change it out and all. Floating number also, that how can we do, like for a 5.5, we can do 4 plus 0.1 and 1 plus 0.5 and all we can do around. Same way, we have to make the floating numbers on also and all. Underflow and overflow conditions also, like we'll be having, we have to make the either side, if it is going to be have more, it's going to be either side is going to be less, so that will say like underflow and overflow, like if it is not going to reach, but limited precision has many expected results now. So now the things will go into the derivatives like a scalar for the derivatives. Like that the measure how much one quantity change when there is a small change in the another one. It's again it's going to be very useful in the case of machine learning and all. It's a simple scalar one. We can just do dy by dx. We can get the how much will with respect to the x how much y changes and all. Then we have the for the vector component we'll be having the gradient. For the scalar we have the derivatives. For the gradient it's a like we'll be having the gradient. And if we have to go with the again like gradient of the gradient, it's called Hessian. Hessian is there. Why do we need to get the like that nature of that particular the problems and all? Because through the change we can get, and if we are going to take what is the nature of either the maxima, either the minima, or maybe there is no correlation points and all. Then one more what we have is the Jacobian form, like it's equivalent of the gradient for the vector valued functions, and Hessian can be seen as a gradient of the go. So then what we have, like these are the metrics that we're going to use in the machine learning and all. Then optimization machine learning technique, like the basic idea behind machine learning is to build a model that will map input to the output data. The thing is that we'll be having some parameter to map the that input to the output. So that should be have for the whole mode that machine as a process that find the best or optimal mode for a given data set and all. So what will be the parameter like best optimal parameter? It will be coming with the hyperparameter optimization, or maybe objective function we have to change it, or maybe that we have to modify or weighted objective functions, or maybe the cost functions and all we have to give it out. So most machine learning problems are therefore ultimately optimization problem. We have to minimize the problem or minimize the error actually. So we'll be having two types of the optimization is there. First one is the unconstrained, and second one is the constrained optimization problem. Unconstrained, like we'll be having a like from the minus to like minus infinity to plus infinity. We have to find out the what is the maximum or minimum. And machine learning actually it's actually only for what I can say minimization problem only. I think I should go a bit fast and then we'll solve that question also. I'll just take one. Okay, we'll go a bit fast only. Unconstant, we have to check with the whole real number line, and it can be done like it can be done with the local that the maximum or minimum only. We have to take the first derivative equal to 0, and to find out the stationary point or critical point, we have to check the whether it's going to be a local minima, or maybe that local maxima or that saddle point. So we have to take the second derivative. It's the Hessian actually, and we put it, if it is coming to the greater than 0, it's going to local minima. If it is less than 0, it's going to local maximum. And if it is going to be a, like equal to 0, it's called saddle point. So for the multivariate and all, it will comes the picture of the like partial derivative and all. Hij like it's delta square f delta xi delta j and all. So it's again local minima, local maxima. It's a positive definite and negative definite and all. It's a Hessian matrix will comes in this picture for the vector. So constraint optimization is again will be having the full within the some limit. Unconstrained will be having minus infinity to plus infinity will be there. So what we have to do? We have to do the either alpha that's the learning rate, or e like error. Make an initial guess like initial weights, and then calculate for the forward one. And we have to make the criteria when do we need to stop, like when the error will be very less and all. So how it worked in the form of like input data is there, output data is there. We have to find out the some sort of relation like that the mapping. So what we have to do, like we have to first to make the relation between the input and output data. So we have to make the hypothesis, and we have to define in terms of the form of the function, and then parameter of the functions like how it will change with the x to the y, and then parameter we have to define, and then that can be done into the either feedback, feed forward, or maybe the feedback also. Like we can go from the uh, initial to the final, or maybe we can come back to the from the final to the initial also. For like a forward modeling, that it's based upon the we have the input, we have to go to the output, like x to the y, we have to go through the it's x to y forward model. If we come back from the y to x, it will become the backward model. And it's like something we are going with the x, the weight we have, and then we are going to define some parameter like that's like a hypothesis, and then we have the ground truth and hypothesis, like then we are going to give some feedback, so it's become the feedback, then we are going to make some decision, like it's the thing. Always we have to improve the results. If it is the error is low or error is high, then we have to make the decisions like this. So what the DL engineer must provide, like they should have that all problems are data and all solutions are functions of map. Then we have to check with the appropriate data set, and we have to choose with the which like forward the forward like that the model, or maybe the form of the loss function list, that's called list square and all, and that optimization algorithm, like we have to use the gradient descent or maybe the Hessian and all. Okay, we'll go. Like we have the two things like classification and then regression fit and all. Okay, will same things are there. Okay. Then what we have, once we're going to run the model, so there chances will be the either sometime the bias will be more, sometime the variance will be more. So we have to find out the optimal way. Okay, bias is more something like we have make some bias, and also it will give the underfitting results, and it will give the overfitting result. So we have to make the some optimal decision. So it will actually related to the model complexity, which is nothing but the number of the parameter and basic function need to be used to the model. So that expectation value of the difference between the model prediction and then correct value. Here expectation is over x and different data set. Once we'll say the variance is something, the variance is the variance on the prediction of the model trained using the different data set. It's called the noise. And if you see around model complexity, when the bias is more, when the variance is more, it's a underfit zone, and this is going to be a overfit zone. And if we talk about the bias and variance, move in the opposite direction as model complexity change. When the model complexity will be less, we'll be having the optimal value of the bias and variance will be there. It's like low complexity, high bias, low variance, underfit. High complexity means low bias, high variance, overfit. Optimal point will be the bias that minimize the total error. How this is how things will go. What is the bias actually? Error between the average model prediction and the ground truth. The bias of the estimated function tells the capacity of the underlying model to the predict the value. The variance is the average variability in the model like a prediction for the given data set, and it will give the value how much the function can adjust to the change in the data set. The same thing what we have talked about. The format. Oh. So that like that is how we can we fix out the bias and variance problem. So initial aspect of the testing set is like insufficient. Like maybe we are doing the 46, 60, 60, 70 and all. Sometimes it will going to make that is, in order to handle the bias variance problem, we need to have following that it will total like training set like 60%, validation can be 20%, and then remaining can be testing for the again for like that only and all. So again, we can do with the regularization. Like it's a complex model with a large number of parameters can lead to the larger variances. So that can be used to like we have to like penalize the larger coefficient value so that underfitting or overfitting is going to take overcome. It's called the regularization. It's the way penalizing the larger coefficient value will is done by the regularization. So it keeps the value of training and test data closer by keeping the optimal parameter. It's going to prevent the overfit. Then we'll start with the linear regression that what we have. It's the y is equal to mx plus c. But again, we can add the linear variable at h, and then j is the cost function, and then we have to minimize this cost function or maybe the error and all. So we have to give the weight, and then it will come to the prediction value and all. So once we introduce the linear activation, non-linear, so we have to give the activation functions that will going to make the sigmoid functions and all. So logistic regression, first one is the like a linear regression. We don't have much of that. We can just simply make y is equal to mx plus c and plus some error. But once we introduce into the some sort of what we can say that like that the non linearity, so we have to introduce the that activation functions and all, or maybe that sigmoid functions or some other function that can be used for the linear regression, used for the regression, and LR can be done for the classification. It's either zero, either true or false and no. So it uses the sigmoid function to convert into the probability value between the 0 to 1. How it done? Like logistic regression, actually by the name itself, it should come under the regression category, but it's actually it's the classification task, and it is used for the segment function probability first and all. So input for feature like a linear combination, then we have the sigmoid function. They'll be able to classify into the binary. So assumption for the logistic regression is the independent observation. Like it's a simple for the like it's the same for the all binary dependent variable, and the linear regression between the independent variable and then log outs and all. Types of the logistic regression is that what we have is the binomial. It's either 0 and 1. Multinomial, it's like we have to unordered classes, and even we can do for the ordinal also, low, medium, and high also we can do around here also. So how the sigmoid function will look like? It's something like this. So when sigma z tends to towards 1, as z in like tends to infinity, and it will tend to the 0 when z is going to make the minus infinity, and delta like sigma z is always bound to the 0 to 1 itself. It's not going to be a like other value or no. So now we'll come to the neural network. What we have is the neural network is like machine learning model that mimic the complex function of the human brain that are going to like we have the dendrites are there, nucleus are there. Once it makes some sort of some input and all, so that through the exome, it the some sort of like output will comes in the picture. That the same way, some input are there 1, 2, 3, 4, and we have to give some through the dendrites and all. We have the linear function, activation function will make some sort of decisions and all. So this is the like this is the one layer. So it will say neural network. Once we have the more than one layer, more than two layer, and also that will become the deep learning task. And here we are using the backward propagation. Here why again will tell you how it done and all. So input layer, hidden layer, and then output label comes into picture. Then we'll come to the CNN. CNN actually it's a special type of the ANN that is going to expect image as an input. Then after ANN, like that to have too many neurons, activation and weight, and an objective function. Since the input is image, so I'll allow it modification to the architecture so that so we can make the sparse connection between the layer and weights are shared between the output neurons in the hidden layer. It means one convolution layer, second one, third one, then the flatten, then we'll be having the again that expansion image will be there. So it can be used for the image recognition, object like detection, and then localization, semantic image analysis now. So what are the architecture of what I can say for CNN? It's the input image. We have to convert into the tensor, and it will come into the matrix form, and it will go with the convolution ReLU. Then again, it's like compression. This is the compression zone, and this is the expansion zone. It's something like we have to making the feature extraction. Then here we are making to the fully corrected layer like classification, and then we are giving the results and all. Okay. So here the image for the like input like it can be image, a spectrogram, a CWT that scalogram also. Okay. So here instead of that manual feature extraction, we can give the directly signal itself or image itself. We like here in the convolution layer itself, they're going to extract the feature. Then we'll move to flatten the layer, then expand it. We'll get the results and all. So now we'll come to the question actually. I'll go through the 10th question. What was the. Shall I solve it? Like, shall I try? Shall I try it like here or we'll do in the last?
So tell,
Sorry?
it's up to you, sir.
Okay. We'll go ahead a bit forward and then in the last we'll try to solve. Yeah. Okay, na?
Sir, I want to just show the my solution to you.
Okay, fine. And like
I
just
am
show it to me. I will just like going to stop the presentation. Okay?
okay, sir. Just I am going to present my screen.
Okay, fine.
This one, sir.
First step is that we have to make that zero
Padding.
matrix. Huh?
Just I am add the padding.
Okay.
This is our image matrix 314749 12 to 14. 3 this is one layer of the padding, second column and two rows. So this is a padding of 1.
Uh-huh.
So now this first element of image matrix 3 multiplied by this kernel,
Okay.
that is 3663. Place here. Similarly, next element is 1 1221.
Uh,
Then next element is 4
4 and then 8,
8
8,
4.
4. It can go.
Because stride is 2,
Yeah.
so we place this at this place.
Just one. Okay, fine. I'll just check it out. And
Okay.
it seems to be that correct only. And then I'll see around. We'll raise the question there also. We'll go ahead. Now we can. This is the feature map, and then from here we what we can get like filters. Like filters is something like in terms of the tensor, like RGB. Like it's a segmentation we can do around and all. And here we can see like a first we see the first convolution. Like we were having the raw image, first convolution, second convolution like block two, block three we can go, and in the finally in the last we can if we are able to give in terms of the RGB with their intensity. Once it's done, so we have to do the flatten. Then from the flatten we can go to the classification task and all. So now here we can see the classification, semantic segmentation, then the classification, and then that we have the localization and all. And here even we can do with the object like detections also. Here we have the cat single object, no object, just a pixel. Here only single object, but here we have the multiple objects. We can do it around and all. So application in image analysis, like it's something like it's a MRI image of brain, and we know that this parameter this and all only. So here the things will comes into the picture of segmentation. Okay, segmentation, like so we have to make the things like here only. We'll take this point, like we can make that this. So instead of going with the all the running on the all, so we can select this portion one, two, three, four, five, six, and all. We can run the CNN. So that's how the that what we can say that advantage of the segmentation will comes into the pictures and all. So how can we do that? Like a parameterization, grayscale image only one, like it can go only black and white. So there is no need to go with the RGB because it's going to be like red, green and all. It's a single channel panels will be there and all. Then what we have is the image parameterization. Like in terms of we have the image with the different color. We can convert into the red, green, blue, and then corresponding their intensity or pixel value. We can do it. So this is the how we are doing in the giving the raw image to the like some sort of tensor forms. So why not regular that the neural network? ANN takes is a like vector as an input, product as an output, another hidden layer, vector carefully connected to the output. For a small image, the number of weight parameter to be estimated are not large, but considered to be 224 by 24 into the 3. It's the RGB image. A single like a neuron, it can output layer have this much weight coming into weight, and a volume of the image. It's like one neuron. It's one, but if the volume of the image, it will explode the number. RGB image will lead to explosion in the number of weights, require more money, computation, or data. So CNN exploit the structure of the data, leading to a sparse connection between the input and output neuron and parameters shared between the neurons and all. So CNN will be going to take operation like a regular ANN type. CNN stack a sequence of the layer followed by a input layer classification. Each layer perform the convolution. It's called a convolution layer, and then pooling will be there. Then opposite will be the pooling layer will be there. The convolution layer, pooling layer are alternatively stacked, leading to a series of fully connected layer followed by a output layer, another 3D volume known as convolution volume. So CNN takes input as an image as a volume, for example, the RGB volume, and sub volume of the 3D medical image, or each record. Like they can take the full volume also, or maybe the sub volume of the like a 3D medical image wherever it's going to use it out. But the ANN input from the each layer another vector of the neurons. Like they're going to take the like a separately and all. So that's how the difference will like a difference will come like a difference will come in the ANN and CNN also. So CNN layer, we have this input image, output with the volume. Convolution layer, input grayscale, output with the volume. Why convolution layer? Like it's something we'll be having the one image, make the layers. And simple cells respond to the edges, line, etc. receptive field like it's from the 1, 2, 3 and all it can make. Complex cells take as input activation from the simple cells, produce the rectified output invariant to the translation. So in that ANN, we can't do the edge classification or edge detections. Here we can do the edge detection by the convolution, like it's something here or maybe here or maybe here by putting the kernel 1 or -1 and all. It's a one example 1 or -1. It can be of anything. So what they will do the operation, consider a scenario by locating the spaceship between the laser sensor. Suppose sensor is going to noisy, like accurate estimation is not possible. So what we will do, weighted average of the location can provide the good estimate. Weighted average of the location, they are going to give the good estimate. So in that what we'll get, XA is the location of the edge sensor, T is the current time, W is the weight. So this is known as a convolution, usually denoted as a ST, is the X into W into T. So in the neural network, terminology, X is the input, W is the kernel, output is refer as the map. So what they will do, discrete convolution can be represented as a X into W into T, or maybe X into W weight of T into -1. Like A is actually a like location or maybe the activation functions and all. What they will do in the once they have done with that, in the neural network, input will be the multidimensional, so it's called cursor, like a kernel. Two-dimensional, it's again it's I into k ij, and then many neural network, it can go with the cross correlation, so no kernel flip is possible and all. So here the 2D convolution is there. We can make it out A, B, C, D, E, F and all. So AW and BX, AW, BX, and then EY and FZ 1. Then so then after BW for second one, BW, CX, then FY, UZ and all. Like it's to converting to the like a 2D convolution type and all. So it that can like from the 1, 2, 3, 4, 3 by 4, it can came 3 by 2. No, 2 by 3. So convolution can exploit the following properties: sparse interaction, parametric sharing, equivalent representation node. So what they will do, like it's something like input what we have is the kernel, output will be there. I think here only that your doubt will get cleared now. It's same way only, but every input every output is connected to the a small like neighborhood in the input through a weight matrix filter or the kernel. We can define the multiple kernels also for the each or every kernel layer. Each gives the rise to the input. Each filter is moved around the input, given rise to the 1 2D output. The output corresponding to the each filter are stacked, giving rise to the input volume. So what is the sparse interaction? So what they will do, like traditional neural network, they're going to use the matrix multiplication to describe how the outputs are there. And so this means every output unit in that interact with the every input unit. But the convolution uses a small kernel, significant reduction in the number of parameter. Computing output requires few, so that the few comparisons and all. So for like for example, if there is a m input, n output, traditional will going to make require m into n parameter, but each of the outputs connected to the at most k unit, number of parameter will go into k into n and all. So what I mean by pooling, typical layer of the convolution that like network, three stages. First stage is actually the layer perform several convolutions in parallel to the produce a set of linear activation. Second stage, run through a non-linear activation function such as rectified linear activation. This stage is sometimes called the detector stage. Third stage is the use of pooling a function to modify the output of the layer further. How it's going to work it out? Input layer, convolution stage like F-line transform, detector stage, pooling stage, then convolution layer, then the next layer will be there. Pooling provides the translation invariance by the subsampling, reduce the size of the feature map. Average pooling and max pooling are like generally used. So here the like that the max pooling, For the 1546, it's become the 6. 8060, so it become 8. 2208, so it's called max boolean. Sometimes we can do the uh, average pooling also. 2 to 4, 8, 12 by 4, 3. It can become. Max pooling is there. 2 by 2 pool size from the 4 by 4. It came to a 2 by 2. Here, average pooling. We make the 12, 12, 12, 12, 48 by 4. It's become 12. Volume convolution is like every layer of the like convolution net has the same API. Take 3D volume of the number, output 3D volume of the number. Size of the output volume or the feature map depends upon the size of the input feature map, kernel size, zero padding or stride. Padded convolution is something like how to do it. Image 3 by 3, convolution 3 by 3, kernel is there. We'll get the 3 by 3 matrices. How we got it? 1 into 1, 2 is to 1, then 1, 0, and all. We can make it out here. We will get like after the multiplication, we'll be getting 5, 10, and 4 with the multiplication and all. Stride convolution also we are going to get in the same way. 5 by 5 is there, and then convolution, then 3 by 3 kernel is there. We can get the same way. Then what we have the CNN architecture, we can get the dense net block. It's the like one type of the CNN architectures and all we have. Then we have the semantic segmentation is something like not just a recognition, labeling as a pixel as a well. Like we have this image, so it's a building. This as a sky. This as the like vegetation, like it's greenery, and then we are having the fence also. Fence, this one as the fence also. Segmentation identifies the collection of the pixel. Here, they are able to building sky, vegetation, or so they're going to identify collection of the symbol and classify them according to the various characteristic. The other two subcategory of the image segmentation are instance segmentation or panoptic segmentation, and all are there. So that image segmentation is like end-to-end image analysis process. Divide a digital image into the multiple segment, classify the informed from the each region. Instance one, focus on the semantic class like contain image that have the entity object like animal and tree. Panoptic is really like more of like a pixel, both of the semantic label where unique, like it's a image base. Why semantic is important? We have to make the distinguish, and it can be used for the AI or machine learning to recognize the pattern, context, photos of the people or the medical images and all. How does it work? Semantic segmentation model create a segmentation map of the input image like 3 to 4 type A, B, C, D and all, and then they're going to reconstruct original image in which each pixel has been color coded by the semantic class to create the segmentic mask. The segmentation mask is actually simple a portion of the image that has been differentiated from the other region. Like segmentation is something like we are going to just divide from the one to second. We have the one original image. Let's say it's a combination of the chair, animal, people, and all. So here, what they will do, they're going to take the pixel, which different color coded, will be going to give it back. It's an image, CNN, building, image, CNN, building, vegetation, and all that can be done. So very inefficient, sometimes will not give the better results. No feature sharing among the overlapping patches and all. So what they will do like dataset for training, it's again same way how they are doing in the like a detailed way. Fully conventional like a network, but we have the upsampling, downsampling. Upsampling will like they're going to increase the size. Downsampling they're going to reduce the size. Max pooling is another critical tool in the process of the extracting the information from the region of an image and analyze them. Max pooling chooses the greatest element in the region being analyzed and all. Application of the segments like a semantic one, we can use the autonomous vehicle, medical diagnosis like a CT scan, X-rays, MRI, and then even we can use for the farming also, photography also. Name-based classification, like name classification for the network. Same way is there, and we'll go with the hyperparameter optimization. Like performance of the network depends upon the various hyperparameter like hidden layer, number of unit layer, activation function, amount of dropout, regularization, learning rate, weight decay, and all. So the thing is that this much parameter is there. So how can we get the optimization parameters? Like in that we have to do the some sort of that method is there. First one is the grid search. Grid search is actually based upon the work possible configuration of the parameter. In that increase the drastically as the number of parameters associated with the increase. It's a Bayesian search also there. Then we have the random search. Rather than that, like training all possible configuration, the network is trained on the subset of the configuration, and then will based upon that also based upon the majority will be going to check it out. So these are the methods for the hyperparameter optimization. Like first one is the grid search, random search. Then what we have is the Bayesian optimization. Like they're going to use the probabilistic model, and then we have that that the meta heuristic genetic methods are also there. It's a handcrafted. It's a advanced hyperparameter optimization now. And then one more concept is there, like we have the one minute. Just 1 minute. Yeah, yeah. I think it's fine now. Is it audible? Hello? It's audible or not? Okay, I'll go. So there is a like that. The next concept what we have is the transfer learning. Transfer learning is something like it's something we are going to pre-train model as we are going to use for the further model. Like method of the like it's something technique that involve reusing a pre-trained CNN model as a starting point for a new related task. Instead of training model from the scratch with random initialization, it's going to help in the when the new task has the limited amount of like label data. Let's say I have like do the sprint training and all. So what can we do? We're going to make some training part, and then we are going to that training I'm going to use for the my competition. So that's how the transfer learning is called in the machine learning. I'm going to use the like a previous or a baseline CNN model and to further that advance into the some like our that is the like that the new model. So modes of using a pre-trained model, CNN that can be used for this feature extractor, remove the classification layer in the like that the network, forward pass through the data and pre-network, and use the embedding. Just 1 minute. Internet is there not? Yeah, is there. Sorry. And then after use the embedding to the like a traditional model, like SVM logistic regression to classify. Then after we can do the fine tuning, initialize the network with the pre-trained weights, and then we can modify the weights. Then we can train the network for the final model. This is called transfer learning. So convolutional network. are data hungry. They need more and more data. Generating an extremely large data is going to be expensive. So in that case, we can use the transfer learning. We can pre-train the model. We can give it the input, that pre-trained model as an input to the exact or actual that model, and then we can get the better results and all. So knowledge of an already trained machine learning model is applied to the different but related problem. How it works? Pre-trained model is there. We can give the freeze the base layer, train the new layer. We can get the fine tuning, and we can get the better results. Retrain the entire model from the scratch, fine tune, retrain, then fine tune. Activation function is something like mathematical function to apply to the output of a neuron. It introduces the non-linearity. Activation function actually going to introduce the non-linearity and all. Without even a deep neural network would have like a simple regression model. Why it is important? Like because in the real world, that data is going to be separable. Like it's not going to be linearly separable. We'll be having some sort of non-linearity and all. And then nonlinear function actually it's allows for the curved decision boundary and making the capable to handling the complex problem like classifying the apple, bananas under the various colors and shape. And this will going to ensure the network model can advance problem like image recognition and then natural language processing and then speech processing. So what are the types of the acquisition function? First one is the like it's called linear regression function. It will be going to use in the regression problem. Then what we have the like a sigmoid we can use in the LR. Third one what we have is the ReLU we can use in the neural network. Like it's a CNN. Then what we have is the TANH or maybe that leaky ReLU. TANH will be there. And ELU graph is the exponential that is there. And we have ReLU is actually used for the where like simply and computationally efficient model help to mitigate the vanishing gradient problem, sparse activation, leaky ReLU to solve the drying problem of the ReLU. Parametric is the like learn the slope of the negative value sigmoid function and then TANH will be there. Learning rate decay. Most techniques tend to decrease the learning rate as number of the iterations got increased. High learning rate parameter value will rapidly and by large amount of the and would not settle down in the local minima. So a low learning rate would lead to the small update convergence to a false minimum. So we should have the optimum learning rate. So model so they should be able to adjust its weight based on the error text. Learning rate decay was introduced which help us to adjust the learning rate during the training. Faster training, it will give overfit results, better convergence, improve the generalization. So this is the one problem is that alpha is equal to alpha naught plus 1 plus decay into epoch. Step decay, exponential decay, inverse time decay, polynomial decay. So one is that here. How can we do the like that normalization and all or initialization and all? So there are a large number of weight in a neural network leading to a large space like search space for minima. So we have to do the weight must be effectively randomly initialized to prevent the convergence of the locus minima. So it's called a zero in like initialization. As the name suggests, all the weights assign 0 as the initial weights as the starting. Like we have to make the 0 0 0. Then we have to we have to update the weights in the coming. Then we have the random initialization like to in attempt to overcome the shortcoming of the 0 constant initialization like random initialization like assign random value except the 0 we can give some 1 or 0 2 1. It depends upon the what we are giving. How can we do the data like normalization? Like that can be done to the z is equal to x minus mu. It's called z z is called like a normalization. We have why do we need the normalization? To ensure the equal contribution of the feature, improve the model performances, accelerate the convergence, and maintain the interpretability or scales. We have the different types of the data normalization. It's called the min and max normalization. X minus x min by x max into x min. We have the decimal scaling, logarithmic transformation, unit vector. Then we have the Z score. It will be x minus mu by sigma. Then what we have the batch normalization. We can do out to fix into the batches. We have the 100 data set. We can make 101 batch, 101 batch, means one batch. Based upon the it's something based upon the internal covariance shift, we can make the batch. It works by normalizing data with each mini batch. This means calculate the mean and variance of the data in which then adjust the values so that have the similar range. Now we'll come to the RNN. RNN is by the name itself is the recurrent neural network. It's basically designed for the sequential data set. Sequential data set is like something it's a continuous data set. Instead of that, we have the discrete data set. It's a continuous one. And they are especially effective for the tasks where context in the order matter, like designed for the sequential and temporal data. Maintain the memory of the past input. It can be used for the NLP, forecasting, or speech task. We have the unfolding, first, second, third. We can get the results. Input layer, same way. Only thing the thing will be having a data set will be based upon the times and maybe the temporal sequence also will be there. And they are going to remember the words that can be came before and then work similar by the remembering the past information and it consider all the earlier word to choose the most likely the next word. So key component of the RNN is the recurrent that the network they hold a hidden state that maintain the information about the previous input in a sequence. Second one, RNN is unfolding, like unrolling the process, expanding the recurrent structure over a time step. It's something like it can come from here, from back there also. Unrolling that enable the back propagation through the back propagation and all. If we see the architecture, like how it will work, we can see it around here. W weight is there, divided into that. Then again we have to give it, expand it, and it will come in the picture. They're going to update in each time step. Type of the neural network, like RNN, that's what we have the one-to-one RNN. One-to-one, it's one single input, single output, single folding is there. One-to-many RNN, single input, 1, 2, 3, like we have the 3 output. Many to one input, like 1 input, 2 input, 3 input. From here, we'll get the single to 1. Many to many, multiple input, multiple output. We can get it out. What are types of the RNN? It's the vanilla, long-term, short-term. Long-term, short-term memory is something, again, it's going to work based upon the temporal data only. Architecture of the LSTM is the similar way what we have the RNN also. And here the weight functions and activation function will be having some different parameters will be there. Then application of the STM, image captioning, machine translation, music generation, auto handwriting generation. What are the problem with the long-term dependency in the RNN? It's going to vanishing the gradient, explode the gradient and all. LSTM architecture, it's going to be input gate, forgot gate, output gate. Control what information is added to the memory cell. Forward gate is something like determines what information is going to remove from the memory cell. Then output gate is something control what information is output from the memory cell and all. Application where we can use language modeling, speech recognition, time series forecasting, and anomaly detection or recommendation system, and then video analysis and all. Then one more what we have is the gated recurrent unit. It's simplified version of the that LSTM that input and out input and forgot the gate into the single update gate and streamline the output mechanism. how it worked, like how RNN is differ from the feed forward neural net, like that network. Feed forward network is processing data in a single direction from the input to the output. Do not store the information from the previous input, and suitable for the task independent of the, independent data such as image classification. Perform purely on the sequential data. RNN is actually include the feedback loop that passes from the information previous step, and maintain the memory designed for the sequential and time independent data effectively for the task where context matters such as time seasonality. It's a we'll be having the way giving, then it came out, again we give the information. It will be go into the one way, not to the two way. Now we'll come to the like a traditional machine learning technique. It's a KNN, binary decision tree, binary regression tree, bagging, and all. So what we have is the suppose like a supervised machine learning, unsupervised one, reinforcement, self-supervised, and then semi-supervised and all. So what do you mean by regularization is something like using the machine to prevent the overfitting, which otherwise causes the model to perform the poorly on unseen data by adding the penalty for the complexity. Regularization encourages simpler and more generalized model. It will going to add the concept to the model to reduce the risk of the memorizing the noise in the input. Like it's improve the generalization, underfitting, appropriate fitting, overfitting. Types of the regularization is the first one is the lasso. It's called L1. What they will do, list absolute synchronous and selection operator. It adds the absolute value of the magnitude to the coefficient as a penalty. It adds absolute value of the magnitude coefficient as a penalty in terms of the loss function. Penalty can shrink some coefficient to the zero, which help in the selecting only important feature and ignoring the less important. Like it's a L1. Then what we have is the L2. A regression model that uses the L2 regression model, it's called ridge regression. It added the squared magnitude. Here, absolute value. Here, squared magnitude. It's called the ridge or L2. Then what are the parameters that we can evaluate for the that matrices? But we have the for the classification. Accuracy is there, true positive, true negative, and then total. This is the what I called confusion matrix. Precision will be true positive, false positive. Recall, true positive, false negative. F1 score, it's something 2 into precision into recall, precision plus recall. A specificity is something like another important matrix is that classify the model, particularly in the binary classification. It measures the ability to the correctly identify the negative instance, true negative, false positive. Then type 1 error, type 2 error. Then we have type 1 error will say false positive, type 2 error will say false negative. Then area under the curve, false positive like a true positive rate and false positive rate will be there. Then we have the validation. Cross validation is something, it's technique used to check how well a machine learning model perform on the unseen data while preventing overfitting. It works by splitting data set into the several parts. Let's say 5 part, so 20%, 80%. Then 20 hold, 20 and all. It can go. So hold out validation, it's called measure typically 50% of the data. It's going to be like twofold. Leave one out cross validation. It is method to train on the entire data set except for the one data point. Stratified, k-fold, 5-fold, 4-fold, 3-fold and all. Then k-fold classification, like it's something test data. This is all for the training. It's for the training, you know. Benefit of the regularization, it's like a prevent overfitting, enhance the performance, stabilize the model, prevent the complexity, handle the like a multi-collinearity, promote the consistency, you know. Now we'll come back to the traditional machine learning technique. Like it's the k nearest classification. They're going to make based upon the Euclidean distance. The model look as the closest data point, like neighbor point, to make the prediction super simple based on the similarity and all. It's like that matrices is based upon the Euclidean distance. Multiple class we can do full remission, partial remission, like did not like survive. Then we have the decision tree is the supervised machine learning technique used for the both classification and regression. Also, it is a hierarchical tree structure which consists of the root node, branches, then the internal nodes, leaf nodes. Internal nodes represent the attribute test, branches represent the attribute value, leaf node represent the final decision result. Root node, decision node, leaf node, decision node, and all. How it works? The model check condition like age, gender to split user into groups. Each groups get a prediction score based on the user performance. It's based upon the gene index and then entropy. What are the types of the like where we can use the finance, medicine, machine learning also, education also. How can we make the decision? Gene index is there based upon the entropy only. How it works? Income is there. If it is yes, what is the age, more than age, purchase or no purchase? No purchase, it's going to make the decision. Information gain, gene index, and then entropy. What are the types of the decision tree that we have? The ID tree, C4.5, CART, like classification and regression trees, chi-square automatic interaction like a detection, Mars, and then conditional interference tree is there. Okay. Then what we have the bagging. Bagging which comes into the ensemble learning. Bagging is something like we have to make based upon the majority. Like we have the multiple decision tree as there, bootstrap, and we'll make the decision based upon the like that the majority votes. In classify the task, final prediction is decided by the majority vote, like the class chosen by the more best voter. For regression, it's going to average across all the modes known as bagging. Bagging is going to versatile can be used for learners such as decision tree, support vector, neural network. Ensemble broadly classify, combine that multiple model to create a stronger predictive system, leveraging the collective strength. Classifier, ensemble classifier, based upon the bootstrapping, aggregation, bagging. Bagging help improve the accuracy and reduce the overfitting by especially in models that have the higher variance. Bootstrap sample, like it's something we have to make the voting like one group, second group, third group. Then we will make the decision based upon the averaging or maybe the majority votes. We can see around here class 1, class 2, majority voting class 1. So we will giving the for the class 1 classification. Out of bag evaluation also we can do out. Binary regression tree, it's like something will be having the average for the regression, majority for the classification. Random forest is something like you have to make the decision tree 1 tree, 2, 3, 4. It can number of tree based upon the again voting the majority. Then will come the class output and all. It can be used for the like high accuracy, handle missing values, work with the large data set like reduce overfitting. Single decision tree, here number of decision tree is more. Like create the like how it works. Create the many decision tree. Pick the random feature. Tree make the decision, and then for the category we have to make the prediction based upon the majority. Modification to the bagging. Grow decision tree from the multiple like a bootstrap sample. For every tree, split consider one random data set, and then learning a random data set to reduce the correlation between three. It's something bagging plus feature randoms. Bagging plus boosting in the learning. It's can bagging can be original data set, bootstrapping, aggregation, like it's a majority. Boosting will be for each classifier, we have to give the weight. Again, going to like train the model. Again the weight, again the model. It's something. It's a plus feature mapping, or maybe the weighted ones. It's called boosting. It's a modification of the bagging only. Bagging will be something will be having the reduce the model variance by training multiple model on a different random set. It can model accuracy by training model subsequently. Here 1, 2, 3. Then separately, then majority. Here, sequentially 1, 2, 3, 4. Use the bagging where your model is overfitting and high variances, especially with the dysentery. Use the boosting when the model underfit and want higher accuracy by learning the complex pattern. Okay. Types of the boosting algorithm. Gradient boosting is there, XG boost is there, kata boost is there. Advantage of the boosting is the improve the accuracy, robustness, the overfitting, handle imbalance, data with better interpretability. And okay, we'll go with the unsupervised machine learning is something will be we don't have the data set will be there, and that data set will be not the labeled one, and we have to make the based upon the clustering and all. So clustering will be algorithm group the data point into the cluster based on the similarity or differences, and we can use the k-means clustering based upon the ages, based upon the popularity, populations and all. K-means clustering groups similar data points into the cluster without needing the labeled data. It uses the uncovered hidden pattern when the goal is to organize the data based upon the similarity and all. Working, we are given the data set item with a certain feature, and then tasked to categorize those into the groups. Effective with the k-means, it's the number of clusters we can say. We can choose the initial centroids, assign point to the nearest centroid, repeat, update the centroid, repeat until the convergence. It's again they're going to use the Euclidean distance. Why to use it's going to use for the simplicity like data segmentation, image comparison, document clustering, organized data. What is the hierarchical clustering? Is that what we have is the unsupervised machine learning that group data into the tree nested cluster. One cluster, two cluster, three cluster and all. Then even we can use for the dendrogram also. Central limit theorem that we are going to use for the once we have the MLE and MAP. That's called maximum likelihood estimation. Maximum absolute posterity and all. So PDF tell us how likely different outcome are for the condition variable, while MLE helps us to find the best fitting model for the data we observe. And PCA will come into the picture like curves of the dimension. When we have the more number of dimensions, it will not get the better results and all. So one dimension there's 10 position, two dimensions 100 position, three dimensions it's going to impact it too many feature, lead to the worst performance. Number of training example requires the increase exponentially with the dimensionality. So PCA it's going to demonstrate like a dimensionality reduction technique which help us to reduce the number of feature in the dataset while keeping the most important information. It changes complex dataset by transforming correlated feature into the smaller set of the uncorrelated feature. How it works? Multiple class with the dominant one. Standardize the data with using the normalization, and then we have to calculate the covariance, and then we have to find out the maximum covariance like most spread, next best direction, perpendicular to the PC1 and so on. That's how PC1, PC2 we can create the data set. Support vector machine they're going to create a hyperplane that maximize the distance between the two class like this. One class, second class, we have to maximize it. MAP and best maximum app posterior like it's a earlier we were having that MLE maximum likelihood function. It was the absolute we have to find out the estimation, but here we have to incorporate the probability based upon the history posterior and then prior. Posterior probability is the revised or updated probability event after taking into the account new information. Comparison between the maximum MLE, MAP, it's something without considering the prior knowledge, but MAP can, they are going to take prior knowledge also. Bayesian regression, they're going to incorporate the like a probabilistic, like a probability and all, or maybe they're going to take the uncertainty into the pictures and all. Then we have seen like a supervised one within the like a data label. Unsupervised like Canon and all. We don't need we don't have the data label. Now we can check it out with the generative model. Generative model is something like we have to regenerate the data set, or maybe we have to regenerate and then discriminate, and then we have to do the predictions. How it work like here. Input, we can get the output. Input, we can get the output like this. How it works, where it can use for the application, for the everywhere we can use for the generative AI. How it works, we have to generate, we have to discriminate, and then classify. I'll show you how it. We are having the example. It's a random input we will give. Generator, fake image will be going to feed the real image. Then we have the discriminator, real fake. If it is fake, we have to give again to the fake image, and until unless it's going to mimic to the real image. How it works, generate the fake data, discriminate the data, feedback loop based upon the like a discriminator, we can get it out. So create a new data similar to the real world data, go beyond classification to generate the content used in the art, image, healthcare, and data science. That we can see around now that they are using the chat GPT and all they are using. Generative AI, synthetic data, generative versus like a discriminator, adversarial training, realistic output. Here outcomes, supervised machine learning, minimize error, regression classification. What is the architecture we have? We have the generator that is that to generate the fake image. We have the discriminator to classify whether it's going to be a real fake and how it's going to work. Latent random variable generator, give the generator condition correct. If it is not correct, we have to give it back. Then what we have is the auto encoder. It's like something we have to time series data that we have. First, we have to give the input like this, and then we have to first encode it, then decode. We will get the like recursion. Like it's a latent variable or underlying variable of the data that inform the way data is distributed, but are not directly observable. Like let's say I have the signal that we can't see through the that naked eye. So we what we'll do, we can use the auto encoder and all. How it will look like, I'll show you. Input data, we don't know the pattern. The pattern. We have given this is the encoder, bottleneck, data was encoded. Now we have to decode it. We'll get the reconstructed like this one, this one. So we have to minimize the reconstruction error. Then what is the architecture? What we have is the encoder, decoder, then latent space distribution. Okay, so I think with this, one more thing is there. We have the Monte Carlo simulation, like what whenever we'll be having in any model that we have that uncertainty, and in that case we have to add some either the noise, white noise, or we have to remove some data and all, so that we can use it out. It generate the many different scenarios to give the clearer picture of the range of the possible results and all. So Monte Carlo simulation following this basic step. What is that? Define the problem, then give the input, run the simulation based upon the data that we have the missing, and then analyze the results. Okay. So I think that's all from my side. If any doubt and all, you can ask around. And this PPT I will upload in the drive folder along with the previous PPTs and all. Okay. So I think we can wind up. Is it? Hello? Are you there? Yeah, fine. Please do feedback, fill the feedback form and all. And give and thank you for the 12-week patience that you were learning. If any feedback and all, can you give it